William Barnas from Bielefeld University. He's going to talk to us about multiphase flow.
Okay, thank you very much for the opportunity to talk here, and also thank you for giving me the opportunity to participate in the program. It was very enjoyable. So I will talk about phase field models. What a surprise for multiphase flows. And there will be quite a lot of overlap with Christian Kalle's talk, and some aspects will be also common to other talks. For instance, I will use the KIP simplex. So I will skip over some details. So this is the outline of the talk. I will start with a short introduction. Then most of the time I will talk about two-phase flows. And in the third part I will talk about how to extend these phase field models for two-phase flows to three-phase flows, and finish with some conclusions. So the idea behind the phase field model is as usual. So we have two fluids separated by a sharp interface. As we can see here, this is replaced by a diffuse interface with a bit that is controlled by a model parameter epsilon. These diffuse interface approaches have a number of advantages which are good when one wants to model fluid flows, multiphase fluid flows. For instance, one can describe multiple fluid phases in a straightforward way, as we will see later. Physical effects like contact angles, surface tension effects, they can be also easily included in the model. The approach can handle topological changes and preserves mass. So these fluid flow problems, of course, they are quite important in many applications. So there exist alternative methods. So I just briefly go over some of the most popular ones. So one of them is so-called volume of fluid method. Then level set methods, we heard a plenary talk yesterday in the morning. Then Lattice-Boltzmann methods are quite popular in applications as well. And then also there is a class of so-called direct methods which track this interface between the fluids directly, but this has disadvantages that the topological changes cannot be dealt with in an easy way. Finally, all of these methods that I mentioned here, as far as I know, they have been applied, maybe except of the level set methods, mostly to two-phase flows, and the extensions to three-phase flows is not trivial. There is another approach that I learned about just recently, is a so-called density functional theory, but I don't know much about this one. It seems that it's computationally quite expensive. But this one can also handle flows with multiple phases. So I'll start with a sharp interface model, since all of the talks were just about phase field models. So to talk about something different, so we have the usual density-dependent Navier-Stokes, incompressible Navier-Stokes equations, and the density evolves according to the mass balance law. The notation is the usual one, and we assume that the densities are constant. So we have two fluids with density, one fluid with density ρ1, viscosity ρ1, and the other fluid with density ρ2, viscosity μ2. If we want to consider surface tension, then we have to impose the following jump condition across the interface between the fluids. One could approximate numerically this problem. Then we would have to deal with this interfacial condition explicitly, which is not always straightforward. And I mention here two works that, of course, this model has been studied numerically for many years already, but the first numerical works where also convergence is proven, that was by Liu and Walkington, who also proposed this reformulation of density-dependent Navier-Stokes equations, which is useful to get the energy estimates then on the numerical solution. And the second one was also my work with Andreas Pohl, where we considered a slightly different numerical approximation. So this is then the phase field approximation. So we have here again Navier-Stokes equations with on the right hand side we have the gravity, and this is the surface tension term. So it's similar as in the previous talk. And then we have the Canhilliard equations here. So we have an order parameter that describes the different phases. We have some advective term, and so these are the usual Canhilliard equations apart from this advective term. And then we have this homogeneous free energy, which I will discuss on the next slide. Then we have some parameters in the model. So the parameter epsilon, this controls the thickness of the interface. Then we have a mu, which is an so-called elastic relaxation time. So that's a phenomenological parameter that keeps the interface width constant. And we can take the generate mobility, as we will see later. At some numerical experiments, I will explain why we would like to sometimes use the generate mobility. And the density here is now not piecewise constant, but is computed as a linear function of the order parameter, which is continuous and varies smoothly across the interface. Okay, so I already mentioned briefly that the order parameter has constant values in the pure fluids. Then we have a diffuse interfacial region where the parameter is strictly less than 1, and the interface is represented in this case as a zero level set of the order parameter. Then we have this potential, the derivative of this potential of the homogeneous free energy, which guarantees that our solution is bounded below 1 in absolute value. And there are several choices that one can take. One approach is to take a smooth potential, for instance, a double well one. And I mentioned here a few names of people that have taken this approach. Another possibility is to take a non-smooth potential. So in this case of the double obstacle or non-smooth potential, this derivative has to be is just formal, and the equation has to be interpreted as a variation inequality. And this is the approach that me and Robert Nürnberg have taken, and also the group in Hamburg. They are dealing with this problem. But we are taking a slightly different approach that I'm going to explain. So maybe a few things that are interesting from the modeling point of view. For instance, it is often necessary for applications to impose a contact angle. So for instance, we have here a solid wall, there is one fluid, and there is a droplet of other fluid adjacent to this solid. And depending on the interfacial properties of these fluids and the solid, we can have different contact angles. And in this model, the contact angle is simply modeled as a nonlinear boundary condition, which is very easily implemented in the numerical approximation. For the chemical potential W, we just take a homogeneous normal boundary condition. So that's one physical effect that can be easily incorporated in the model. Other boundary conditions are also possible. So this phase field framework allows for different modification via the free energy approach. So for instance, we can take a dynamic contact angle, which has been proposed by Chuck Min, or one can also deal with contact angle hysteresis. So some work has been done by the people mentioned here in this area. So more complicated phenomena can be also incorporated in the model. Surface tension. So the surface tension is a force that lives at the interface. In the phase field framework, this is a body force. So there is no special treatment of the interface needed in order to impose this force, and we take it in the following form. There is a relation between this formulation and the jump condition for the sharp interface. So we have this jump of the stress that you have seen on in the beginning across the interface, which is proportional to the curvature. And in the level set approach, we can approximate these quantities using the level set function. The order parameter can also be interpreted as a level set function, and so we have the normal to to the surface, which is just a gradient, normalized gradient. Then we have the curvature that can be computed in the following way, and then we have delta function. So there is this continuous surface tension approach that is used in level set formulations to impose surface tension, and this can also be mimicked in the phase field formulation, as has been discussing in this paper by Kim, where he compares different surface tension formulations for two-phase flows. And for instance, in the phase field, you should be actually see. So the order parameter can be interpreted as a level set. So all these quantities, such as normal vector and curvature, can be computed in the following way. And then we have the delta function. There we take an approximation of the delta function in the following way, where alpha is a scaling parameter that has to be suitably chosen. And then the analog of this level set approach in phase field models is this one, which is actually equivalent to this term up to some correction in the pressure in the Navier-Stokes equations. So there are different possibilities how to model the surface tension. And now let me come to the numerical approximation. So we want to solve this model numerically, and then we approximate the time derivatives by the usual backward differences. For the Navier-Stokes equations, we use also the Taylor-Hood elements, so quadratic for the velocity, linear for the pressure. For the Canihede equation, standard piecewise linear elements. So here are the finite element spaces. Notice that for the Canihede equations, we take these finite element spaces of functions that are bounded by 1. And then the numerical approximation is as follows. And here I say just a few remarks. So it's essentially very similar to what you have seen in the previous talk. We also need a reformulation in order to get an energy inequality. So these terms in the Navier-Stokes equations, they have been replaced. So it's a semi-implicit discretization. Some quantities are taken from the previous time level explicitly. And the last equation, where we had the derivative of homogeneous free energy, which was non-differentiable in the obstacle case. So we do not regularize this equation, we solve it directly, and therefore we have to then deal with this variation inequality. So this is a linear variation inequality. So that's the difference to the previous approach. The advantage of this approach is that really the order parameter is now strictly bounded below plus and minus 1, which is not necessarily the case if one takes the smooth potential or regularizes the potential. But we have to then develop suitable solvers for this problem. Okay, so we can also obtain an energy estimate for this problem. At least for the constant density and viscosity case, we can show convergence along the lines of the works of Feng and K. Stiles and Belfort, which was done for the smooth potential case. I mentioned the density-dependent models of Abels, Gartke, Grün, and the convergence analysis that was done by Grün recently. So our model is different, so we don't have this nonlinear flux term there, but we still can get an energy inequality by the reformulation. But it's not clear whether this reformulation somehow complicates things when one wants to prove convergence for the density-dependent equations, because then it's not clear where the numerical solution is converging. At least we could, I think, there is a hope that we could show that we can that the solution converges to this reformulated problem. Then the system that we obtain by numerical discretization is a semi-implicit discretization, but it's a still coupled system of Navier-Stokes Canihede equations. And in the numerical approximation, we have to solve this nonlinear system, so we decouple it by simple fixed point iteration. So the complex terms, which are nonlinear, are simply taken from a previous iteration, and we iterate until we obtain some convergence. Also, we use some mass lumping. And also, for this advective term, for stability reasons, mainly for the than for the linear solvers that we use. We add an upwind term there, so some numerical diffusion, which is not a problem because anyway the model keeps the thickness of the interface constant, as you will see when I show some numerical experiments. So then these fixed point iterations have the advantage that the equations are decoupled, so we can use dedicated solvers to solve the Navier-Stokes equations and the Cahn-Hilliard equations. So for Navier-Stokes equations, we use a multi-grid approach, which is good for 3-dimensional simulations. In 2 dimensions, it's sufficient to use just a 2D solver, which is in fact faster. And for the Cahn-Hilliard equation, so now this is the Cahn-Hilliard variation inequality. So for this we use, we adopted the algorithm of Graeser and Kornhuber. So this is some kind of active set solution strategy. And there are also other approaches. We have developed a fully nonlinear, if you want, well, it's not nonlinear multigrid, but fully obstacle type multigrid for this problem, but this is less robust. I would say that the active set strategy seems to be more robust and preferable in this way. Also, we are using adaptive measure refinement, so the order parameter is constant in the pure fluid, and then there is a sharp variation in the diffuse interface, so it's natural to use fine resolution within the interface. And the implementation has been done in the final element code Alberta. Okay, so I will show you now some experiments. So the first experiment is a response to a question posed by Charlie Elliott when I presented this some years ago, the first results, and he asked, so if you take 2 circles and you let them evolve, what's going to happen? So do you already know what's going to happen? So now we have a rotation and velocity field, so they will be rotating. So let's see what happens. So they rotate, and you can see the interface is preserved. So this is there is a lot of work on the solution of advection equations where people want to minimize the numerical diffusion. So here we have no numerical diffusion, the classical numerical diffusion, but there is the Cahn-Hilliard diffusion. And what will happen is that the smaller bubble will be absorbed in the big one. And I used to show this as an example of non-physical behavior of the model. But in fact, then at one time, someone in the audience told me that this can also happen in the fluid flows. So this is the Oswald ripening. So sometimes this may not be desirable, this behavior, but it can be switched or it can be dealt with by taking the degenerate mobility. If one takes the degenerate mobility, then these 2 droplets would be rotating forever. So then there are some examples of rising bubbles. So the 2-phase flow. There's a bubble, that's air bubble that goes up in water. So different example. So air bubble goes up. Then a layer forms and bursts. Here you can see the effects of the surface tension. So the stronger the surface tension, the more circular the bubble stays. This is the benchmark problem that we have also seen previously. So what is interesting about this benchmark problem? So there are 2 problems. One is let's say the easy one, and the other one is the hard one, where the parameters, where the flow is a bit more rough. The interesting thing is that all these methods that were compared for the second problem, the harder one, they do not really converge to the same solution. Then this problem was not so long ago computed with the phase field model by Allen and Boyd, and they show that in fact even different phase field formulations for this problem converge to the similar solution even in this case. And so in order to test our code, we have also computed this one. It's a little bit slow. So the bubble is going up, and then here at the tips, 2 bubbles will detach. It's really a bit too slow. So they detach, And then also you will see here, it's hard to see, but there are some artifacts here. So there is some mass left, which stays diffuse because it's not, the thickness of the interface is quite thick. That indicates that somehow, probably with a small epsilon, so thinner interface, there might be that there would be some other smaller bubbles formed with this next to these bigger bubbles. So you can also solve three-dimensional problems. So this is a problem where you also can see the cut through the mesh. So this is the adaptive mesh. So this is again, these two squares will rotate. So they will quickly become circular and rotate. So in 3 dimensions, it's a little bit difficult to deal with the Navier-Stokes equations in the formulation that we have. So we use just the P1 elements for efficiency. We were also interested in porous media flow, where all these surface tension and contact angle effects play an important role. And I will show you the following video. So of the so-called fingering. So if there is a strong surface tension and under a certain contact angle condition, the flow via the porous medium, so these are square pores with some random perturbation. So then the fluid will find some preferential paths and will form so-called fingers. So the flow is not uniform, but with these fingers, and it's quite interesting to watch. So there has to be some pressure has to build up in these pores, and then the fluid chooses the easiest way to proceed. And here you can also see the adaptive mesh for the simulation. Okay, so now I come to the extension for more than 2 phases. The first equation is more or less the same. So there's the Navier-Stokes equations. Then we have a surface tension term, and now we replace the Canihilide equation by a multi-component Canihilide equation. So for each phase, each phase now will have its own order parameter, and the order parameter should be positive, and the sum of the parameters should be 1. So these are natural constraints for this problem. Now instead of the mobility constant, we have a mobility matrix. Then the potential here, or homogeneous free energy, is taken again of an obstacle type with a matrix here that models the contact angles, and we take again an obstacle energy. So the numerical treatment is really analogical to what I showed you for the 2 phases. It's again, we again have to deal with the variation inequality for the Canihilide part. And again, so the equations are decoupled. And in this case, the Canihilide equations are solved by the Bloch-Seidel method, which was developed by Robert Nuremberg. So in each step, we solve a block of all the variables that are associated. So for an n-component system, we have n degrees of freedom for each element. So we take this n elements and solve this small system here, and then we have to project this solution that we get in order to satisfy the constraints on the solution. So numerical experiments. So here you can see 3 phases. So this is a rising bubble. All the phases have different densities. So this is the air. If you want, this is the oil. So there's lighter one than the water, so it goes up. And then what is nice about this model that we can introduce these contact angles at the triple junctions in the model, which is not, as far as I know, except of this density functional theory, the level set method and volume of fluid methods. This is not possible to do in a reliable way. I mentioned here a few works, related works with the smooth potential, and this is a work on these are works on the Canihilide with obstacle potential numerical approximation. Of course, there are more, but I don't mention them all. Okay, so I think my time is slowly running up. So one thing I wanted to, so I'll show you 2 more experiments. So this is a test or a demonstration of the effect of the interfacial tension in this multi-component model. So these are 3 bubbles, or we have 3 materials. So this red one, blue one, and the gray one. So the fact that there is a gray color here is just an artifact of visualization. So that's there is no gray material around here, and it's difficult to see. But well, the difference between the pressure inside this bubble and outside should be proportional to the curvature, and here the curvature is smaller than here, so the jump should be less, and it's not visible, but you can also see that the difference between the two is smaller than between the two other droplets. It's not possible to see this on the projector, unfortunately. So this is just a qualitative demonstration of the interfacial tension, how it works in the canonical model. I will conclude now with some remarks on this approach and on the numerical approximation. So these phase field models have the advantages that they preserve the mass, they can deal with topological changes, with multiple fluid components, so not only 2 but more. We can easily include different physical effects via the free energy in some rigorous way. However, it's not clear what is the physical interpretation of this width parameter and the mobility. So these parameters have to be somehow chosen depending on the problem, so either by the computational resources or also on the problem, because this mobility coefficient acts as it preserves the interface, but if the flow is very rough, then the interface can be distorted. This can be corrected by taking larger parameter, larger mobility, but what this means physically is not clear. So in the future, we would like to extend this approach to really get good efficient solvers so that we can solve 3D problems efficiently. We would like to have a closer look at the density-dependent problem for the multi-component flows. For instance, a corresponding thermodynamically consistent model for this formulation does not exist yet. What is open is convergence analysis of the numerical schemes for the density-dependent model, and some other aspects such as optimal control, where we have already taken some first steps, and also people in Hamburg around Michael Hinze, and multi-scale flow in porous media, where these models seem to be quite interesting from the point of view of application. So thank you very much for your attention.
Questions? Yeah. Is there a sharp interface limit for the sharp interface version?
Sharp interface limit has been shown for this for the model of Gartke, Grün, and Alant. So they show that their model converges to the sharp interface model depending on the parameters. They can recover the sharp interface model that I have shown.
For the multi-component.
For the multi-component, no. For this one, no.
Is there like a classical sharp interface?
No.
As well. No. Okay.
For the I'm guessing, but I guess just for the Canhilliard part, I think there is some work done, or there should be. So, but I would not know immediately.
Your interface, in particular in the picture where one bubble was absorbing the other one, seemed to be quite thick. So how small can you make a Repsol one in your numeric? So
it depends. It depends on your computational resources. So in 2D, typically we can take the epsilon 1/64 pi. So this maybe says something to people who are familiar with the model. And that means for this problem we take a mesh size that is 1/256. So if you have a square 1 by 1, then you divide it by 1/256 in 3 dimensions, so that's quite a bit less. There we can, let's say, comfortably handle problems where we have a mesh size of order 1/3264.
So your rising bubble. I think Robert has recently done a sharp interface calculation of that rising bubble. Is that right? With unfitted finite elements and triangulated.
I'm not aware of that, but it would not surprise me. So I think he has done some work.
Quite interested to compare
Yeah.
your phase field computations with.
In this original paper, when the benchmark is proposed, they use a sharp interface approach to compute the problem, and in any case, the results obtained with the sharp interface limit differ from the level set computations.
Yeah, see, I mean, what I remember we heard from Robert, is when you had this ghost mass, didn't you?
Yeah.
That you left.
Mm-hmm.
You had a very, very thin,
Yes.
like a jellyfish type.
Yeah, I think that's probably an indication that that he's getting similar results as what phase field does, but okay, he cannot do the topological change.
Okay, there's no more talks. Can I thank all the speakers this afternoon?